What if the black hole at the center of our galaxy isn't a black hole? That's not clickbait. That's the literal claim of a new peer-reviewed study published in February 2026. For decades, Sagittarius A star has been the poster child for supermassive black holes. We have measured its mass, tracked its stars, and even imaged its shadow. But this new research suggests that every single one of those observations could actually be explained by something else entirely: a dense core of fermionic dark matter. Before we go any further, let's separate three things: what we absolutely know, what this new model proposes, and the specific observation that could prove it wrong. Because this isn't black holes don't exist. It is a competing explanation for one specific object. And the scientists behind it aren't saying they've proven it. They're saying the current data can't tell the difference. So in this video, you're going to see three layers. First, what we actually know is there: the stars, the motions, and the famous shadow image. Second, what this new fermionic dark matter model is trying to explain, from the inner light-hour orbits to the outer halo of our galaxy. And finally, the decisive tests. What observations would clearly separate a true black hole from a dark matter imposter? And here's the kicker. There's one very specific feature, called a photon ring, that could kill the dark matter scenario almost overnight. You can't visit the center of the Milky Way, but astronomers have been watching it for over 30 years. In the late 20th century and early 2000s, two teams, one based at the Max Planck Institute in Germany, the other at UCLA, turned the world's biggest infrared telescopes towards the constellation Sagittarius and started tracking the motions of individual stars packed around a tiny, bright radio source called Sagittarius A star. These so-called S stars, especially a star named S2, trace out huge, elongated orbits that swing incredibly close to whatever is sitting in the middle. At their closest approach, some of these stars are only light days from the center and are moving at thousands of kilometers per second, up to around 10% of the speed of light in the most extreme cases. If you've ever seen a planet orbiting the sun drawn in a textbook, the same basic gravity still applies. In very simple terms, the orbital speed v of something bound in a roughly circular orbit is related to the central mass m, and the radius r by v squared is about g times m over r, where g is the gravitational constant. You don't need the math details here. The key idea is that for a given distance, faster orbits mean more mass hiding inside. When astronomers plug the measured speeds and distances of S2 and its neighbors into this relationship, they get an enclosed mass of about 4 million suns, all crammed inside a region smaller than our solar system. And whatever is in there is dark. There's no bright cluster of stars, no glowing ball of gas. Just radio and infrared emission from hot materials swirling around an invisible center. That's why, for decades, the simplest explanation has been a supermassive black hole. It's compact enough, massive enough, and dark enough to fit the bill. The work measuring these orbits was so convincing that Reinhard Genzel and Andrea Ghez shared the 2020 Nobel Prize in Physics for it. Then, in 2022, the Event Horizon Telescope, an Earth-sized network of radio dishes, released the first image of Sagittarius A star, a fuzzy golden ring of radio emission with a darker patch in the middle. That dark patch is interpreted as the black hole's shadow, the region where gravity bends light so strongly that fewer photons can escape toward us. Put all of this together, and the case for a black hole looks extremely strong. Fast stars, tiny region, enormous mass, and an image that matches black hole simulations. So how could dark matter possibly fake all of that? To understand the new claim, would you first need to know what kind of dark matter we're talking about? Dark matter is a catch-all name for whatever invisible stuff makes up about 85% of the matter in the universe. It doesn't emit light, it doesn't absorb light, but it does feel gravity. Most of the time you hear about it as a huge diffuse halo surrounding galaxies, helping keep their rotation curves flat so stars don't fly off into intergalactic space. The team behind this new study is working with a particular dark matter model based on particles called fermions. Fermions are a broad class of matter particles that includes electrons, protons, and neutrons. The crucial property is that fermions obey the Pauli exclusion principle. Two identical fermions can't sit in exactly the same quantum state. In plain language, they can't all pile into the same spot in exactly the same way. That you can't all sit on top of each other rule gives fermionic matter an internal pressure, sometimes called degeneracy pressure. It's the same basic quantum effect that helps support white dwarfs and neutron stars against collapse under their own gravity. In this model, if dark matter is made of very light fermions, that quantum pressure can stop the dark matter from collapsing all the way into a black hole, even when it gets extremely dense in the center of a galaxy. Over the past decade, a group of researchers has developed what's called the Ruffini-Argüelles-Rueda, or RAR, model of fermionic dark matter. In this picture, the dark matter in a galaxy doesn't just form a big, featureless halo. Instead, it naturally settles into a structure with two parts: a very dense and compact core at the center, and a more extended, diffuse halo around it, both made of the same fermionic dark matter particles and linked as a single, continuous system. Here's the key twist for the Milky Way. If that central core is dense and massive enough, its gravity on nearby stars would look almost identical to that of a supermassive black hole. From the point of view of star orbits, it doesn't actually matter whether the 4 million solar masses are in a black hole or in a tiny ball of ultra-compact dark matter, as long as the mass, size, and shape of the gravitational potential are about the same. In 2020, a study in astronomy and astrophysics showed that the orbits of S2 and another object, G2, could be fitted using such a dense, fermionic dark matter core surrounded by a halo, without needing a central black hole at all. And that work suggested that, at least in principle, a quantum-supported dark matter clump could play the role usually assigned to Sagittarius A star. The new 2026 study pushes this much further. Instead of focusing only on the inner light year, it asks a much bigger question. Can one and the same fermionic dark matter structure explain both the violent dance of the S-stars near the center and the large-scale rotation of the Milky Way's outer halo? To see why that's such a big deal, you need to zoom out from the galactic center to the outskirts of the Milky Way. Astronomers measure how fast stars and gas orbit at different distances from a galaxy's center and plot that as a rotation curve: speed versus radius. For many spiral galaxies, these curves stay roughly flat a long way out, and which is one of the classic reasons dark matter was invoked in the first place. If gravity came only from visible stars and gas, you'd expect orbital speeds to drop off more steeply, what's called a Keplerian decline, like planets in our solar system. For our own galaxy, getting a clean rotation curve is harder because we're sitting inside the disk. But the European Space Agency's Gaia mission, especially its third data release, Gaia DR3, has finally given astronomers enough precise stellar motions to map the Milky Way's rotation out to more than 20 kiloparsecs from the center. Analyses of that data have found signs of a genuine Keplerian-style decline in orbital speeds in the outer halo, dropping by roughly 30 kilometers per second between about 19 and 26 kiloparsecs, and ruling out a perfectly flat curve at high statistical significance. And that's awkward for some standard cold dark matter halo models, which often predict more extended, slowly declining halos. But it's exactly the kind of behavior that a more compact, fermionic dark matter halo can produce. In the RAR framework, the same parameters that set up a very dense, central core naturally lead to a halo with a sharper edge and a more rapidly falling rotation curve at large radii. The 2026 Milky Way study takes this seriously. The authors treat the Milky Way as one continuous dark matter structure, a fermionic core at the center, plus a halo that extends through the whole galaxy. They tune the dark matter particle mass and the internal parameters of the model so that the halo matches the outer rotation curve measured from Gaia and related surveys. Then they ask, with that same setup, does the inner core reproduce the observed orbits of the S stars and the dusty G sources near Sagittarius A star? Within current observational uncertainties, the answer is yes. In their statistical analysis, the dark matter core model and the conventional black hole model fit the S-star data about equally well. And because they have already matched the Gaia-based rotation curve at large radii, they argue that this single fermionic structure might be explaining two very different regimes at once: the chaos of the inner light days and the graceful rotation of the outer halo. This is the part that makes theorists sit up. It's not just maybe the black hole is something else. It's maybe the thing anchoring our galaxy and the dark halo we normally treat separately are really two faces of the same, our exotic dark matter distribution. But what about the image? If you've seen the famous orange ring of Sagittarius A star, it sure looks like a black hole. How could a ball of dark matter possibly fake that? Here, the story leans on another piece of work from 2024. A separate team took the same family of fermionic dark matter cores and asked a simple question. If you put a glowing accretion disk of hot gas around one of these cores and trace how light rays bend in that space-time, what does the image look like for an observer far away? When they ran the simulations, the result was surprisingly familiar. Strong gravitational lensing around a very compact dark matter core created a central dim region, where light paths are strongly deflected away from the line of sight, surrounded by a roughly circular ring of emission from the orbiting gas. In other words, a shadow-like structure that looks strikingly similar to the Event Horizon Telescope's images of Sagittarius A star and of the black hole in the galaxy M87. From the point of view of a telescope with limited resolution and dynamic range, like the current EHT, that ring plus shadow pattern could be extremely hard to distinguish from a true black hole shadow. The bright ring comes from gas orbiting near the compact object. The dark center comes from light either being swallowed by a horizon or strongly bent away by extreme gravity. In both cases, you get something that looks like a glowing donut with a dark middle. This is exactly why the press releases around the 2026 Milky Way study lean so hard on the shadow comparison, and the lead author describes it as a pivotal point. The dark matter core model doesn't just fit the rotation curve and the star orbits, it's also consistent with the famous black hole shadow image. In their words, the dense core can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. So if both a black hole and a dark matter core can give you fast orbiting stars, a 4 million solar mass central object, and a ring and shadow image, how do you tell them apart? This is where the science gets really interesting, because the two scenarios are not identical. They differ in ways that future instruments can, in principle, detect. The first key difference lives right at the edge of the would-be event horizon, and a true black hole does more than just bend light. It allows photons to orbit in nearly closed paths very close to the horizon. Some of those photons loop around the black hole one or more times before escaping to the observer. This produces a series of extremely thin, sharp features in the image called photon rings. Nested bright circles corresponding to light that has orbited once, twice, 3 times, and so on. In the fermionic dark matter models studied so far, those stable photon orbits do not exist in the same way. There's no event horizon, and the spacetime doesn't create the same kind of photon trap. As a result, when researchers compute images of these dark matter cores, they find that while you do get a shadow-like central darkness and a main bright ring, you do not get the same clean, infinitely stacked photon ring structure that a black hole should produce. Here's the catch. With the current generation of the Event Horizon Telescope, those ultra-thin photon rings are probably below the level of what can be cleanly resolved. The EHT images we have of Sagittarius A star mostly show the overall ring size and shape and the broad brightness depression, not the delicate substructure. That's why both a black hole and a dark matter core can still be consistent with the data. The authors of the 2026 study explicitly highlight this as a falsifiable prediction. In their own summary, they point to photon rings as a key feature of true black holes that should be absent for dark matter cores. If future, higher resolution EHT-style arrays can cleanly detect such rings around Sagittarius A star, it would be a strong blow to the dark matter imposter scenario. If, on the other hand, the images remain compatible with a shadow, but show no sign of the expected photon ring pattern, even as imaging improves, that would tilt the balance toward exotic alternatives. The second key test comes from even more precise measurements of the inner star orbits and relativistic effects. Instruments like gravity on the Very Large Telescope Interferometer in Chile already measure tiny relativistic precessions and redshifts in S2's orbit, subtle shifts that depend on the exact spacetime geometry around the central object. Both the black hole and dark matter core models have been tuned to fit the current S-star data within the error bars. But they predict slightly different detailed behaviors for things like how pericenter precession changes over time, or how orbits of different stars are correlated. As gravity and future infrared interferometers push the precision of these measurements, tracking more stars closer in over longer baselines, the two models should pull apart. The 2026 paper actually stresses this point. With current inner star data, you cannot decisively distinguish between a black hole and their dark matter core. That's why they lean strongly on the combined fit to both inner orbits and the outer rotation curve to make the case that the dark matter picture is worth taking seriously. But they also emphasize that upcoming gravity observations and searches for photon rings are exactly what's needed to test it. There's also the broader context. The 2022 EHT analysis of Sagittarius A star already used the observed ring size, as together with very precise prior measurements of the central mass from the S-star orbits, to test general relativity. Within current uncertainties, the ring size matches the predictions for a Kerr black hole in Einstein's theory extremely well, and the team used this to place strong constraints on a wide class of exotic alternatives with hard surfaces or different space-time metrics. The fermionic dark matter core scenario isn't obviously ruled out by those constraints yet, partly because it's been constructed to closely mimic the same mass-to-distance ratio and lensing properties. But it has less wiggle room than you might think. As images improve and multi-wavelength data pile up, any alternative model has to keep threading a tightening needle. It must reproduce the star orbits, the spectrum, the variability, the ring size, and eventually the photon ring structure, all in one coherent framework. So where does all this leave Sagittarius A star? Right now, the cleanest, simplest explanation for the 4 million solar mass object at the center of the Milky Way is still a supermassive black hole. It's the picture that fits decades of stellar orbit data, general relativistic tests, and high-resolution imaging with the fewest new assumptions. The fermionic dark matter core model is a bold alternative, but it's also a very specific one. It doesn't claim to overthrow black holes in general, or say that dark matter definitely replaces Sagittarius A star. Instead, it offers a unified way to connect the Milky Way's inner dynamics and its outer rotation curve using one exotic dark matter structure. And it shows that, within current uncertainties, that structure can masquerade as our galaxy's central black hole. From a scientific point of view, that makes it valuable, not because it proves the black hole is fake, but because it sharpens the questions. It tells observers exactly what to look for. If future EHT upgrades clearly detect the thin photon rings that are unique to true event horizons, the dark matter core idea at the galactic center will be in serious trouble. If gravity and its successors measure S-star orbits and relativistic effects so precisely that only the black hole spacetime fits, the conventional picture wins decisively. But if, as instruments improve, the data continue to be compatible with both pictures, or even start to favor a more compact, a sharply edged halo when you combine the inner orbits with the outer rotation curve, then the idea that dark matter is faking our galaxy's black hole will move from fringe speculation to a serious contender. In other words, the real story here isn't astronomers were wrong about the Milky Way's black hole. It's that our best tools have become sensitive enough that we can now test, in detail, whether the object at the center of our galaxy is the simplest thing general relativity allows, or the first direct glimpse of dark matter behaving in a way we've never seen before. Either way, the next decade of observations at the galactic center is going to tell you something profound about gravity, about dark matter, and about how far we can push our models before the universe forces us to rewrite the script.